Now we're going to go to session 2, and now so we're moving from market opportunity to technological approaches and interventions. And our first speaker is going to be Jim Delosio. And Jim is a principal with Kepler, Hahn, and Hyatt, a 28-person structural engineering, landscape architecture, building envelope service firm in Syracuse. He's also former chair and current member of the ASCE SEI Sustainability Committee and a former USGBC National Board member, and has been a principal investigator for research on thermal bridging. Jim, welcome in, and at about 4 minutes, I'll give you a 1-minute warning, and then at 5, I'll let you know to be wrapping up. Thanks.
Okay, thanks. I hope you can all hear me okay. This is carbon counts, calculating the carbon content of commercial construction in 5 minutes or less. Taking it down from a 90-minute presentation. Okay, next slide, please. And I'll be done in 5 minutes. I've been practicing this. Okay, repeat of some of the things we've heard about earlier today. Portland cement is a pretty big contributor in the construction world of embodied carbon, 5 to 7%. We got 6 billion cubic yards placed every year. Okay, next slide. But thanks to industry aggregated, next slide, please, environmental product regulations, declarations, we can actually aggregate what the carbon emissions are from concrete. The National Ready Mix Concrete Association put out an EPD in November 2019 of many, many different batches from different batch plants across the country. And you can concatenate it and summarize it. It's about 1.3 pounds of CO2 for every pound of Portland cement in the mix. And that varies from about 450 to about 850 pounds per cubic yard. I think we need to get some solid metrics, an understanding of what we're doing when we place a yard of concrete, whether it's for a sidewalk or a tall building structure. And this is cradle to gate, with the gate being the batch plant. Then you've got to add something for delivery, placement forms, all those workers coming to finish the concrete and all. Okay, next slide. And we can do the same thing with steel as well. The American Institute of Steel Construction put out EPDs of various different structural products, cradle to gate being the fabrication shop. It's about 1.5 pounds of carbon emissions per pound of structural steel. That's a real simple metric to get your head around. So you got 1,000 pounds of steel, you put out 1,500 pounds of CO2 into the atmosphere, plus erection and then waste and end-of-life impacts. Okay, next. And you can do the same thing with any construction material, really. Wood is more complex, but the American Wood Council put out an EPD 2013, a number of years ago. It's about 0.15 pounds of CO2 per pound of wood emitted. And it's complicated, but we're not including any biogenic carbon, like the stored carbon in the material for that 0.15 pounds. It also doesn't include waste, scaffolding, erection, construction, and end-of-life impacts. Okay, next. And so what I did is I designed a hypothetical, theoretical, 100,000 square foot, 10-story rectangular simple mixed-use building. This is the construction vernacular of the early 21st century, at least in my world of buildings, okay? And what I did is I developed this real simple spreadsheet. I call it a carbon palette. It's got the carbon emissions from the third-party verified environmental product declarations. And you can tally the, next slide, please. You can tally the carbon emissions per project in a pretty straightforward way, just by including the amount of materials multiplied by the carbon emissions. I actually included a small factor for waste and construction impacts. And the bottom line is this 100,000 square foot building puts out about 3.5 million pounds of CO2 emitted. This is ballpark, but it's pretty close. You know, it's within 1 or 2%, I think, using the standard EPDs. That's about 35 pounds a square foot for the building structure alone from the embodied carbon. Okay, next. And so when you have a simple thing like this, you can look at, next slide too. That was my exciting animation. Then you can kind of tweak the options and look at optimizing the concrete, optimizing the steel, using a little bit of fly ash. And I like using frost-protected shallow foundations when possible to reduce the volume of concrete. So real simple cost savings measures that you can take and see what that means in terms of the carbon impact. Okay, next. And that turns out to be about 3 million pounds of CO2 emitted for that building, which is about 29 PSF, a little bit down. So we can get the metrics. Okay, next. And then we can do what I call transformative improvements and change from steel to wood, cross-laminated timber decking, floors, walls, and roofs, glulam beams and columns, and really get 50%. You really get reduction of concrete usage using concrete optimization, which you can do 50% supplementary cementitious materials, and really drill down and change some things in a kind of a transformative way. And with this, okay, go ahead, next. Not including, this is all wood, but not including biogenic carbon, that brings it down to about 2 million pounds, which is about 19 pounds a square foot from the structural system. Okay, next.
1 minute, Jim.
Yep, good, this works well. And then there's a thing called biogenic carbon. Next please. Every pound of wood, 19% moisture content wood, represents about 1.5 pounds of atmospheric carbon dioxide stored from in the growth cycle of the tree. And so next, what we can do is, assuming biogenic carbon and assuming end-of-life impacts from the wood that we use in the materials, then we can actually do a quick summary of where we are with the different options. Yeah, next, please. Okay, next. Forgot about that one. Yeah, this is the summary, including the transformative reductions. It's actually a negative carbon footprint, including the biogenic carbon. Now, it's controversial, and not everybody agrees on the numeracy of the biogenic carbon, but it does have some value in the marketplace. Next one, and it's the last slide, I think. So we can do a quick comparison. We can come down in increments, we can come down transformatively, or we can include some of the benefits of the biogenic carbon. These are the 3 different options, and the next and final click on the slide will show, instead of the transformative 1.95, it's actually a negative 990,000 pounds of carbon. Imagine a building that is built with negative carbon emissions. It is possible, and I think that we need to all get more educated about the metrics of carbon. That's my 5 minutes. Thank you.
Jim, thanks so much. Good to hear about the work, the carbon counts, and this notion that every material we use, we can actually figure out the carbon impact of in useful ways in building use. And then you walked us through this great example of from traditional to incremental improvements to transformative, and then even tossing in biogenic carbon so that we can see from really large carbon emissions to negative carbon emissions from our building construction. It's quite impactful and gives us a sense of what's possible. So thank you so much, Jim. And I think we have a second presenter here, correct? What's the next slide, Caitlin? Going.
The next presenter is Peter Rose. Here we go.
Great. Yeah. So Peter Rose is a recognized leader in the architectural design profession. He began his practice in 1978 and received numerous awards for residential, institutional, and urban design projects of very large scale. As you can see him here. Peter, welcome. And as with Jim, I'll give you a heads up at 4 minutes and then let you know when you hit 5.
Oops, I'm having trouble with hello, hello?
Yeah, Peter, we can hear you.
Okay, good. Thank you very much. It's wonderful that NYSERDA is doing this, and I find it all fascinating. So I'm assuming it's strangely silent here, but let's just, someone will let me know if you can't hear me.
We can hear you.
Okay, good. I have been for about 10 years, 11 years, my office and I, and partly also as an academic, have been working in the realm of timber, engineered timber, mass timber. It began when we did a competition called Low to No, Low Carbon to No Carbon, for a master plan for a kilometer square of Helsinki. Our proposal was basically to build 8,000 housing units out of timber. It was the very beginning for me, beginning to understand how these systems and processes could work. I had many interesting collaborators, but a critical one was a guy named Matthias Schuler, who's one of the founders of Transolar, a firm of engineers and physicists. They call themselves Transolar climate engineers. So way back then, we were looking at how to make, in this case, a community for 25,000 people that would be carbon zero. We had in 2015, did a big research into housing. We were hired to disrupt the housing industry by a financial institution, and we persuaded them that we needed to understand housing broadly, the history of housing, but particularly the history of construction. And that intensified our focus on timber. Similar collaborators, Transolar certainly, Nippers Hellbig, another German firm, and we're also interested in housing. We're interested in how expensive it is, how not very good it is, and the timber began to lead us not just to issues relating to climate change and carbon, but means of industrializing the process, making the quality higher, the time of erection far less, and making it cheaper. The goal was better housing, better and cheaper housing. Next, please. Oops, I need another slide? Somebody pushing a button. Hello, hello.
We're here.
Okay. We're here. Okay, good. So, mass timber engineered. I like the term engineered timber. It's wood. It's a new material, but it's an old material. It's wood. It looks kind of low tech. Again, wood. It's hard to think of wood as high tech, but it's super high tech. From the time that a tree is cut and becomes logs, to the time that you see what's in front of you on the screen, it's almost labor-free. It's highly driven by computers and computer programming and robots and robot-driven processes. Next, please. And this is just the sort of standard stuff about the issues relating to carbon and carbon emissions in the building industry. And the timber interests us on a number of levels. The fact that it also addresses carbon emissions. I mean, that's at one of the core things. Next, please. I have no idea how many minutes have gone by. And so, as all of you know, much more scientifically and much better than I, the use of timber in buildings is a way of storing carbon and doing something not just to slow down the emissions of in the making of a building, but in fact to go the other way. Next, we got to keep rolling here. And so what we are interested in basically, we're looking at housing at scale, industrialized, modular. Actually, modular is our focus, has been our focus for a long time. And you can make a building that stores about as much carbon as a sort of one of the buildings that's been discussed in previously in this process with steel or concrete. We think that you can, with a similarly sized timber-based building, industrialized timber, modular timber, you can offset the carbon in at least one steel or concrete-based building, possibly two. Next. So I'm going to just take you through very quickly. So this is snippets of a very elaborate series of models that are the beginning of a process of making buildings in a very particular way. So we're interested in 6-story buildings, which the code more or less allows, with a concrete podium. Perhaps one doesn't need the concrete podium. I still have a deep affection for concrete. And this is just showing 2 stair towers and 2 elevator cores in the middle. The stair towers can be of wood. Next, please. So there is a way of making components in a CLT factory that can be flat packed like an IKEA bureau and shipped to a place where they can be assembled in a relatively low-tech fashion. And this is just showing one of them. Next, please. And next. So this is just, this represents, these 3 boxes are a 1-bedroom unit that we've done. Next. And so that's 6 boxes. Next. And this is 30 boxes, and boxes, modules, whatever you call them. We are working on making these so that almost everything is in them. The finishes, with the exception of the floor, the fixtures, the plumbing, everything but the hookup. And you can do, we have colleagues in Europe that we're working with. It's precise enough that you can install 30 a day. Well, 10 a day is easy, 30 is pushing it. But if you do them vertically like this, next please, you have a weather enclosed process. So the roof is there. This is 1 day's worth of work. The side is Tyvek. Next please. And that you just blast along. Next. And we working with TransSolar on all of the energy systems. The goal is to take a 6-story building. This is 55 units of housing, a mix of studio and up to 3-bedroom on a podium, but off the grid is pretty achievable, and carbon positive is achievable. And that's it. We're working intensely on this, and with a bunch of people that we are hoping are going to implement things like this. That's what I know. I have no idea. I'm sure that was more than 5 minutes. Sorry.
It's all good, Peter. It was very helpful. Thanks for sharing your